Good afternoon. Am I audible? We will wait for a few minutes for others to join. Okay, we will start the session. Welcome to the live session 6 for the NPTEL course Basic Environmental Engineering and Pollution Abatement. With me, Mahalakshmi S, Research Scholar from NIT-Trichy. So this is the general information. This live session for the course Basic Environmental Engineering, Pollution and Abatement will happen every Saturday from 3 p.m. to 5 p.m. You can join the class by using the same Gmeet link. Please note down this link. You can join the class every Saturday from 3 p.m. to 5 p.m. using the same Gmeet link, which is MDI VDCP NCG. And all the live session videos will be uploaded on the YouTube channel where you can access the videos later. The channel name is Mahalakshmi S. You can find it through at Mahalakshmi Shekhar NATT. So we will first discuss the previous week assignment solution, which is for week 5. And for this week, week 6 lectures overview will be given. After that, we will solve some sample questions for assignment 6 and we will solve the problems related to the week 6 lecture. So now coming to the first question from the assignment 5, it is which air pollutant is or separated by gravity settler? So what is a gravity settler? So it is a settler where you can see the inflow and outflow of the pollutants. So all the gas pollutants will be going in through this settling chamber in and out. So we can observe the settling of the pollutants here based upon the gravity. So this is mainly applicable to the particulates. So that is the right answer. In the case of gas molecules, these are mainly separated by two different processes called absorption and next process is adsorption. So the air pollutant separated by the gravity settler is the particulate. So these are the particulate matter. It is separated based upon the gravity-based settling here. And the gaseous molecules are in general absorbed or adsorbed by using the solids and liquids. Right answer is particulates. The second question is the collection efficiency is normally defined as. So here, what is this collection efficiency telling us? Collection of the gaseous pollutants. So these are the gas pollutants. Okay. So where these will be collected in which method? Any idea? So this is related to the collection of the particulate matter or any other pollutants going through any settling chamber. Like it can be a gravity-based settling or it can be a electrostatic precipitator. So whatever the medium, so the collection efficiency here refers to the removal of the particular material. So it is obtained by using this relation, which is efficiency. Total efficiency is equal to 100 into weight of the material collected divided by the total amount entering into the collector. So the collection efficiency is defined as eta T is equal to 100 into weight of the material collected divided by the total amount entering into the collector. So in the case of ESP, which is electrostatic precipitator, these materials are collected in between the plates. So there will be a electrostatic medium. So when this gaseous pollutant are passing through this electrostatic medium, so these are all connected to electric field, right? So where the metal rod will be there ionizing the gaseous pollutants. So here there will be a collecting surface within this metal rods. So whenever this pollutants are passing through here, once it is charged, it will fall down and it will be collected in this plate. Amount of material collected here and the total amount entering. The ratio between this will give the efficiency. So now the next question is, in the Stokes law region, drag coefficient CD is in the range of dash. So what is the range of drag coefficient in the Stokes law they are asking? What is the right answer? Anyone knows? So the right answer is CD less than 1. So this is the range of drag coefficient in the Stokes law ratio. Next is which of the following is or types of electrostatic precipitator. So electrostatic precipitator shortly termed as ESP. So this is charging of the gaseous pollutants by using the electric field. So whenever the pollutants are getting ionized, they will be collected in the collecting field. So this can be of different types. The right answer is A and B. So there are two different methods. One is the parallel plate precipitator and the other is the wire and pipe precipitator. These are the types of electrostatic precipitator. This precipitator is mainly for the particulate matter. Next question is identify the instrument given in the figure. So this is the instrument. So in this instrument, the dirty gas is going inside through the inlet and then it is going inside each and every chamber here. So vertical alignment here are called as what? So these are the bags, filter bags. So there are n number of bags. Within this bag also there will be different regions. After passing through the each area of this bag, all the clean gases will be emitted from this outlet. And then the dust particles will be collected here and they will be get deposited in this region finally. So this is a fabric cloth filter bag. So this instrument is fabric filter. So all the fabric filter, gravity settlers, cyclone separator, ESP, everything is to collect the particulate matter. Now the next question is what is the typical efficiency of a fabric filter for separating the fine particles from a gas stream? So they are asking about the efficiency of the fabric filter. As we have discussed in the week 5 lecture, fabric filter will be having the higher efficiency. The total efficiency of the fabric filter is very high when compared to the electrostatic precipitator. So the maximum amount of efficiency is 99%. Next to that comes the electrostatic precipitator. Yes, second is the right answer. The next question is which of the following is the disadvantage of a wet scrubber? So wet scrubber is used again for collecting of the gaseous pollutant. So in this one, what is the major disadvantage of wet scrubbers? They are asking. So relative low energy cost is an advantage, and then simultaneous removal of gas and particulate matter is also an advantage. Here the corrosive problem is the one of the disadvantages. So in the wet scrubber, what happens? We will be using many fluids. So what happens? The fluids are when they are coming in contact with the gaseous pollutant. When though we are removing them then and there and collecting the dust particles from them, since the reaction between them might cause some corrosive problems in the instrument. So this is the major disadvantage of wet scrubber. Next question is which of the following equipment is used for removal of particulate? So, as we discussed, all the gravity settlers, electrostatic precipitator, and fabric filters, all of these are used for the removal of particulate matter. So, the right answer is all of these. Now, coming to the problems, calculate the plate area. So, they are asking you the collection plate area. So, this is where the gaseous pollutant, that is the particulate matter, is collected. Calculate the plate area of an electrostatic precipitated ESP, removing 85% of particulate matter. So the efficiency of this ESP is given. So eta T is 85% from the exit gas of a cement industry having 200 ppm. So the concentration of particulate matter is 200 ppm. Assume the exit gas flow rate. So the flow rate is given, which is Q, right? So the exit gas flow rate is given as 150 meter cube per second, and the drift velocity particles is W is equal to 0.11. So the drift velocity is given, just W, and the flow rate Q is given, and eta T efficiency is given. They are asking you to find the area of the collection plate. The right answer is 2587. So it is derived by using this formula, where the collection efficiency eta T is equal to 1 minus e power minus W A divided by Q. So this area is the collection plate area, W is the drift velocity, and Q is the flow rate of the exit gas. So all the values are known here. We have to find only A. Eta T is also given, which is 85%. So 0.85. So substitute all the values. So 0.85 is equal to 1 minus e power minus 0.11 into A divided by 150. Then we have to rearrange this equation, which is 1 minus 0.85 is equal to e power minus 0.11 A divided by 150. So we need to take logarithm on the both sides. So take ln on both sides, and ln of this is equal to minus 0.11 A whole divided by 150. So ln of 1 minus 0.85 is 0.15. The value will be negative. So negative negative sign will get cancelled. We have to rearrange this, and the A1 will be calculated. Just nothing but the plate area of an electrostatic separator. So the answer is 2587. The next question is to calculate the sedimentation rate in gravity separation for the particle size limiting to. So the limited particle size, limiting particle size is d lim is equal to 7 micron. The particle density is given as 1040 kg per meter cube, and liquid density is given as 1000 kg per meter cube. And the viscosity of the continuous phase is given as 2 into 10 power minus 3 Newton second per meter square. So viscosity mu is given, and the particle density is given, uh, and then the liquid density. So the particle density is solid. So this is the liquid density, and then the diameter d is also given. So only thing asked is to find the sedimentation rate. So what we have to do is we have to use the formula of free settling velocity, which is Qg is equal to dp square into rho s minus rho l into g divided by 18 mu. We know the diameter of the particle, which is 7 micron. So 7 into 10 power minus 6 the whole square. Rho s for the solid it is 1040, for the liquid it is 1000. And then G is constant, which is 9.81 divided by 18 mu. So mu is 2 into 10 power minus 3. So I am taking it as 0.002. If we solve this one, the answer will be 0.534 into 10 power minus 6. So this is the sedimentation rate in the gravity separation. So this is the sedimentation rate in the gravity separation. We have to use this formula, which is Ug is equal to dp square into rho s minus rho l into g whole divided by 18. With this, you can find the unknown value. So now coming to this week 6 lectures. The first lecture is 26, which deals about the groundwater and surface water. So the treatment of groundwater and surface water are discussed in this lecture. The two major sources of our daily drinking water is one is the kind of stagnant water, which is groundwater. These are all from the sources like shallow well and deep wells around the houses. And the next one is the surface water. So these are all the running stream waters, right? So these surface waters can be river water, lake water, or it can be from a reservoir. So how these surface water and groundwater are treated in general is discussed here. So this is a table showing the difference in the treatment steps for the surface water and the hard groundwater. We will discuss in detail in the next slide. First, we will look into the steps along. So the first step is screening or microstrainer. So this is simple straining method like we do in our house. So this straining is the removal of the solid particle, that is a larger solid particle, and then the pre-sedimentation or pre-chlorination. This is a pre-treatment step, and then comes the rapid mixing. So we are adding the chemicals and we are going to mix the surface water, and then a slow mixing followed by the rapid mixing. That is a slow mixing so that all the unwanted particles will get separated. These are allowed to settle under gravity, so the sedimentation process comes. And after settling, we will be again filtering it. So the filtration process is to separate the solid and liquid. Then adsorption is optional process to remove the organic content to make it taste better and improve the color and odor. Finally, the disinfection happens. So in the case of hard groundwater, we can see the first step is aeration. So we are providing more amount of air into the groundwater, and then we are trying to oxidize it. We can either do oxidation or we can do a pre-chlorination step as in surface water. The next one is rapid mixing. Instead of using the coagulants, we will use the lime and soda for this rapid mixing. Then it is followed by precipitation. So here the floccules are formed. Here because of adding the lime and soda, precipitation will occur. Followed by sedimentation and recarbonation. Recarbonation here is to improve the quality of water. So we are purging the carbon dioxide here, and then comes the filtration. Finally, disinfection is done before it is allowed to drink the groundwater. So, if we see the steps involved in the treatment of surface water in detail, so the first step is rapid mixing. So, in the rapid mixing, as I said, the blending of chemicals are happening with the water for treatment. We will be adding different chemicals based on the type of water and based upon the pollutant levels. And for this mixing, we are going to use a material called impeller. So this impeller is a agitator. It is used for mixing the chemicals in the water. So how long this water is going to stay in this mixing tank means? So the retention time is at least for 1 to 2 minutes. So the retention time is at least for 1 to 2 minutes. So if you look into this picture, we can see the different kind of impellers used. So this is the impeller region. Okay. So this is the mixing tank. That is a reactor. Into the reactor, we are allowing that water to flow in. It is called as inflow. And then when the water is passing out of this reactor, it is called as effluent. So we are adding many chemicals into this mixing tank, and we are using the impeller to mix the chemicals with the water. This type of impeller is called a turbine channel. So look at this design. So it will be like this. So this kind of impeller is called as turbine channel. And here, this kind of instrument, okay, this is called as a propeller chamber. So this type of impeller is called propeller, okay. And then this is a double compartment turbine chamber. So it is the same turbine. So we know that this is a turbine. Since there are two turbines type impeller are used, and it is divided into two compartments, it is called double compartment turbine chamber. This is also a double compartment turbine chamber. Here these are horizontally divided into two compartments. Here it is vertically divided into two compartments. That is the only difference. And this is the paddle chamber. So paddle chamber and the turbine chamber has only a limited difference. There will be a space in between in the turbine, but in the case of paddle chamber, it will be like a fan. Okay, so these kind of impellers are used to completely mix the chemicals with the water for treatment. Okay, and this is the inline blender. So whenever the water is passing through the pipe system itself, here there is a impeller. So it is a blender kind of impeller. So it is going to mix it on the way of passing itself. Okay. So these are the different kind of impellers used for the mixing of chemicals with the water in the mixing chamber. So the second step is the coagulation and flocculation. So in coagulation and flocculation, what is happening means alteration of the surface charge of particles. So normally these particles will be negatively charged, and these charges are altered and these particles come together, so that what happens, these particles will attract with each other based upon their charge, and they will, due to the opposite charges, they will be getting attracted and they will form a larger particles, and what happens is neutralization of the surface charge happens. So these larger particles are called as the flocks. So this larger particle, when the particles are getting attracted and they are coming together as a larger particle, they will be easy to separate. So they will be easy to settle down in the water. So that is what happening in the coagulation and flocculation. And then so in flocculation, one of the important thing is slow rotation of the paddles. So when the paddles are slowly rotating, these larger particles will settle down easily. And then the detention time, the amount of time it is going to be present in the population tank is minimum 20 minutes. Okay. So now if you see this process, this is the coagulation process. These are the colloidal particles. The general size of this colloidal particle is in the range of 0.001 to 1 micron. So it is very lesser in size, right? Whenever the particles are very less in size, it is very difficult to separate them from the water. So only we are adding the coagulating agent. So the charges will be occupied around this surface of the particle. They will be getting attracted like this. Each and every small particle, when they come in together as a larger particle, it is termed as the flock, which is in general size of 1 to 100 microns. Since it is larger in size, they will be easily settled down. And the coagulating agent commonly used for this process is called as alum. Its chemical formula is Al2SO4 thrice 14H2. So this, when this alum is added, how it is going to dissociate is it will give the Al3 plus ions, SO4 2 minus, and the water molecules. So whenever it is going to interact with these colloidal particles, it is going to neutralize the surface charge of the particle. And then what happens is, in the presence of bicarbonate, this Al3 plus ions will form AlOH thrice, and it will liberate the carbon dioxide from it. When there is insufficient amount of bicarbonate is there along with aluminum hydroxide. So this aluminum hydroxide here is the precipitate. So it will be easily sedimented as a solid. Okay. So this, along with the AlOH thrice, in the presence of insufficient bicarbonate, it will also produce H2SO4 along with water instead of carbon dioxide. So this is the process happening in the population. So now coming to the next step, sedimentation. So sedimentation is just allowing these flocks, larger particles, to settle down. So settling of particles merely taking place for about 3 hours. So 3 hours detention time is there. So here we will apply the Stokes law and we will find the sedimentation velocity of each particle. What is the settling velocity of the particle? After settling down, we will be the next step is rapid sand filtration. We will be filtering all the sedimented water and the solid from it. So now in this rapid sand filtration, the filtration media is of different type. It can have a single filter media which is full of sand alone, or you can have a separation media of dual media which is having sand and coal in it. So two different medias are there. Next is you can have a multimedia like along with the sand and then coal. We can also have some silica particles like that. That can be a different filter media used in this rapid sand filtration to improve the efficiency. And then the next step is disinfection. So in the disinfection, what is happening is chlorination. So chlorination, as the name indicates, we are going to use the chlorine. So when this chlorine is going to react with the carbonate molecules, it will be forming a HOCl, and then it will be altering the nature of the water. So these waters are disinfected so that no microorganism will grow in the water. And ozonation is is a substitute to the chlorination process. Here we will be using the O3 ozone gas, and in the ozonation process it will reduce the amount of organic content by biological degradation, like excess supply of oxygen will help to degrade the organic matter content in the wastewater, and then it will reduce the turbidity of the solution, and it will also improve the color of the water. So that is why the disinfection is done in general. So now if you see here, after rapid mixing, we are adding the coagulants. By this process, these colloidal particles are forming a bigger flock, and in the flocculation process, these flocks are settling. Okay, so this is the flocculation basin where this paddle is rotated very slowly. So what happens? So these flocks are moved to the settling basin because of the larger size of the flock. These particles are getting settled down here. Okay. Next, only the water with a very small amount of smaller colloidal particle will pass through the sand filter. So in this rapid filtration chamber, you can see they are having a dual media where the coal and sand are used, and gravel is a supporting media. So when this water is passing through this, the small colloidal particles can be separated, and only the fresh water is coming out of the filtration process. So if no flocculation is happening means all the smaller particles cannot be separated in this filter, because when a larger amount of smaller particles are there, these filter will also get clogged. So the clogging will be happening very intermittently. So the filter will get damaged. Since these are all allowed to form as a larger particle, only very small amount of colloid particle only pass through this filter. So the clogging of filter pores will take a larger amount of time. Once these filters are clogged also, we can use back pressure, and we will allow this particle to separate, come out from this filter, and we can regenerate this filter and reuse it. But we cannot do that very often. So only we are going for the coagulation and flocculation process. So if you see this one, this is the schematic representation of the treatment of surface water. So here the surface water is supplied, and then the first step is screening. So screening removes all the larger particles. This is a pre-treatment. There comes the rapid mixing tank. So in this tank, we are adding the chemical, which is coagulant like alum. We are adding it to the tank, so it is mixed, and then it is passed to the flocculation basin. So in this basin, the paddle is slowly rotated, and then the particles are allowed to pass through the sedimentation basin. Once the sedimentation happens, all the larger flocks are collected here and removed as a sludge, and then the water molecules again transported to the rapid sand filter. So the filtration process occurs. After filtration, the treated water is disinfected and it is stored, later distributed. Okay. So now in the second diagram, the only difference is using clarified. So Flocculation is nothing but it is the combination of coagulation and flocculation in a single step. So here, after adding the coagulant, so here along with the mixture, you will be adding the samples. So the sludge will be forming, and then it is again going for filtration. Then it is coming to the storage tank after disinfection. This is the treatment steps involved for the surface water. So in the case of groundwater, what is happening means ion exchange will happen to soften the water. So softening of water means removal of hardness and pathogens. So what is causing the hardness of the groundwater means the two important elements involved are calcium and magnesium ions. So these calcium and magnesium ions are constituting majorly for the hardness. So once these calcium and magnesium ions are removed from the water by using the ion exchange method, like these ions will be captured in the column, so our groundwater will be clean. And the other one is the sodium, excess amount of sodium content, Na plus. So this can be removed by using a brine solution. So we will prepare a brine solution. So when we are passing the brine solution as a 12 phase, so it will carry all the sodium ions in the groundwater. So we can remove all these ions by using the ion exchange process. So this is how the groundwater is treated. So it also involves this step, like groundwater from the wells are passed through the rapid mixing tank and then to the slow basin, then the sedimentation, removal of sludge, and then the only difference is recarbonation. As we discussed earlier, we are carbonating it. Why we are carbonating it means we are giving oxygen to it so that the recarbonation will increase the pH of the solution. How means all the hardness can be removed by formation of CaCO2, which is nothing but calcium carbonate. Calcium carbonate. So this calcium carbonate will precipitate down, and the H plus during this recarbonation, H plus a lot of H plus ions will be liberated. So the pH will increase and alkalinity of the solution will get decreased. So the hardness is also removed in this process. So this is about the treatment steps for the surface water and the groundwater. Coming to the next lecture, it deals about the treatment of domestic and industrial wastewater. So in the case of domestic and industrial wastewater, the treatment is classified into four different methods. So in this one, the first method is the on-site disposal or septic tank system. And the second one is the domestic wastewater or sewage treatment system. And next is the industrial wastewater or effluent treatment system. Finally, the common effluent treatment, which is CETP. So when we will go for this on-site disposal system, so this is a very familiar one, right? So if we are not having sewage lines in our home, what we will do, we will store all the household waste in the septic tank, and then from the septic tank it will be periodically disposed of. They will be carried to the STPs. So this is the on-site disposal system. So this is used where sewers and the centralized wastewater treatment system are not available. When this system is not available, we will go for it. Coming to the domestic wastewater, so through the pipelines, all these wastewaters are collected and it is transported to the STP for the treatment. And this is the domestic waste, the common municipal waste. And in the case of industrial wastewater, it is also similar in manner. But only thing is, if the industrial effluents are alone collected and these are treated in ETPs. So ETP is particularly made for the industrial wastes. Okay, and common effluent treatment is from the industrial cluster. Say for example, that area itself having a lot of industries in a single area. Okay, so in this region, all the industrial effluents will be collected and it will be given to the CETP plant. Like together they will be treated After the partial treatment, these can be again sent to the STPs for further treatment, or else if it is not further treatable and can be disposed into river means, they are again tried to recycle it, and they will be again tried to recycle and use for the industrial purpose itself. So this is the schematic of the septic tank. So what is happening here is the inlet is here and the outlet is here. In between, what is happening is settling of particles. So the settling will allow you to form the sludge at the bottom, and then flotation happens. So slowly, what happens? The water particles alone will separate, and in the sludge, what happens is anaerobic digestion. Since this is a very closed environment. So anaerobic process happens where the microorganisms are going to decompose the sludge and it will be producing lot of gases. So the gas liberated from the anaerobic process is CH4, which is nothing but methane gas, right? So this is how the septic tank is processed. And this is the schematic of the domestic wastewater treatment. There is the wastewater treatment design. So the raw wastewater is first collected from different household, and then it is passed through the screening chamber. So in the screening chamber, all the floating materials are removed and grit and grease removal. So this chamber is to separate the solids, oils, grease from the water. And then comes the primary treatment. So the primary treatment is often a sedimentation of flocculation process. Here in this diagram, the sedimentation is mentioned. So the solid particles are removed as the sludge and it is going to the clarifier. And then the activated sludge tank. So this is the secondary treatment process where we will be using the biological organisms to treat the water. And this is a aerated chamber so that all the microorganisms in the presence of oxygen will degrade the organic content in the wastewater, and the sludge formed is also again collected. And this is the final clarifier where these sludge are again separated from the treated water, and only the pure treated water is allowed to flow through the sand filter media, and finally the purified water is received out here. So in general, these are treated in 4 ways. When there is no pipeline or centralized system, on-site disposal is preferred. And domestic wastewater are going to STPs, industrial wastewater are going to ETPs. The procedure is same, but only the plant is different. So this is the same procedure going to happen there. And a common effluent treatment plant is used for the industrial cluster area where many industries are there. So now, in this treatment of domestic and industrial wastewater, many methods are involved. Like I said, there will be a pre-treatment, there will be a primary, secondary, and tertiary treatment. But within this treatment itself, there are different types. The first type is the physicochemical treatment. So in the physicochemical treatment, we will be screening the larger particles. Then comes the equalization. So equalization is more like aerating. We use different kind of aerators. So whenever you are bubbling through the tank, so we are sparging the air here in the tank. So whenever you are sparging the air, so many gas molecules will be produced. Because of this, what happens? It never allows the solid particles to form a stagnant layer at the bottom. So it will be always floated so that it ensures that process is going well. That is the reason for using equalization chamber. And the next step is coagulation, where we use the coagulants and the flocculation, then sedimentation, clarification. So we know all these steps. Next kind of treatment is biological. So in the biological treatment, instead of flocculation, like instead of using the chemicals like alum, we will be aerating it. So this aeration is mainly to ensure that microorganisms are growing in that wastewater so that it can be treated. That is the purpose of this aeration. It is for ensuring the growth of the microorganism. And next one is the mixed treatment. So in the advanced treatment where the physicochemical and biological treatment methods are combined to improve the efficiency of the process. So this is again a schematic diagram of the wastewater treatment. So the influent water is coming in, and in the pre-treatment it involves screening, grit and fat removal, and these wastes are disposed and only the filtered water is going to the next chamber, which is the primary treatment. So, in the primary treatment, many methods can be involved, the sedimentation of the solid particles can happen, and then skimming of oil and grease. So, the oil and grease are the major problem. So, initially they are removed from the primary treatment itself. So, in this primary treatment, since it is focusing mainly on the solids, so the efficiency is it removes the 60 percentage of solid and 35 percentage of BOD is removed in this step. And in the secondary treatment, we use the microorganisms, right? It is a biological treatment. So it can be an activated sludge treatment or it can be a trickling filter treatment where we use the microorganism in the presence of oxygen. So these microorganisms are going to help you degrade the organic matter content. So the BOD is again increased, right? So it is increased. So the secondary treatment removes 85 percentage of the BOD. It removes around 85 percentage of BOD and solids. Next is the tertiary treatment. So it includes tertiary steps like ultrafiltration or microfiltration. So it is a filtration process. And lagooning by natural wastewater stabilization. It is allowing the filtering of solid and liquid matter. And then the nitrogen phosphorus removal, which is the major reason for eutrophication. So all these are done in the tertiary treatment. So in this step, 95% of BOD is removed and all the solids and some amount of nitrogen and phosphorus are removed. So all the sludge are again treated in the sludge treatment process. Finally, the quaternary treatment is nothing but your disinfection. So disinfection is to ensure that whatever microorganisms are used in the treatment process should not be alive in the drinking water. To ensure the killing of the microorganism, disinfection is happening, which is the quaternary treatment. So the first step can be a chlorination by using chlorine, bleaching. Next is the ozonation where we use the ozone and the photolysis. So it is not commonly used using the light energy to kill the microorganisms. Finally, the treated water, that is the effluent, is coming out of the process. So these are the major treatment steps, types, and method types, and these are the percentage of BOD and COD removed from each process. So next lecture is about the primary treatment equipment. We know that there are different stages. First is pre-treatment, second is primary treatment, third is secondary treatment, fourth is tertiary treatment, and finally disinfection of quaternary treatment. So in this one, what are the equipments used in this primary treatment is explained in this lecture 28. So the first one is the bar rack. So a bar rack is more like a lines. These racks can be vertically arranged or it can be in inclined position like this. It can be in 90-degree also. So this is the example of bar rack. So this is mainly to stop the larger solid particles from entering into the next process. And this grid chamber, this is the grid chamber. It is a narrow plane, okay, narrow plane. So it is mainly to maintain the constant velocity. So the flow velocity is maintained constant by using the grid chamber as a control. Okay, it can be a horizontal flow, a rectangular flow, or a square flow in the treatment process. Next is the equalization tank. We know that equalization tank uses the aerator, so it never allows the solid particle to form a sludge at the bottom immediately. The water particles are mixed again and again here by using the aerators, and it avoids the sludge formation. All these mixed water is going to the sedimentation tank. So in the sedimentation tank, what happens? This is a one type of sedimentation tank. This is a hopper sedimentation tank. So here the wastewater is going in and it is coming out. It has a scraper here. So here the settling will happen. We can collect the sludge from the water and the treated water goes through the top. So the next step is the dissolved air flotation. So this is also another method where we will be using the air for allowing the mixing of the uh, wastewater with the organic matter content. So this is the diagram of sedimentation of the waste particles. So the sedimentation is affected by many factors like the density and size of the particle, temperature of the particular water, and the turbulence existing in the water. All these things mainly affect the sedimentation. So this sedimentation happens at different stages, but one thing you should observe is this graph. So with respect to time, uh, this sedimentation tank should be left undisturbed for some period of time. With the increase in time, the depth of settling will also increase. With increase in time, the depth of settling will also increase. Say for 10 minutes, the first particle is here. Okay, in minutes. After 60 minutes, it can come to the final zone. Like the settling depth will be higher when the time increases. So we can see a clear water region here. And then what happens? The first stage is discrete settling region. So in this region, what happens? All the particles will be settling down at the same velocity, more or less. And in the flocculent settling region, what happens? Here we have added the quark length. So the interaction will be happening between them. So they will be interacting. So it will come down faster relatively. And then in the hindered settling region, here the reaction is complete. So larger flocks will be formed here. So the larger flocks will be formed here. Each particle is of different size. So again the velocity of settling will decrease slightly. The rate will decrease. And finally what happens? They will again come to the compression region. Once they are reaching the end of this stage, the settling will be faster. So these are the different regions of settling in the sedimentation tank. And now this is the diagram of dissolved air flotation. It is nothing but we are using the pressurized air. Here is the air drum. The compressed air is coming here in contact with water. So the air completely saturated with water is purged here. So under the pressurized condition, the water is purged. And again, air sparger is here. So air is also allowed to come to the atmospheric condition. So it is the difference in this pressure. Here in this flotation tank, the water is here, baffle rods are here. So this water is completely uh, mixed by using the baffles here. And with the interaction of this air sparger, the air molecules will allow the water constantly to be mixed. And then what happens? The sludge is collected down and the pure water is flowing out as the effluent water. Here we are using the saturated air as a medium for separation. So whatever air supplied here will help in the decomposition of the organic matter in this flotation tank itself. That is how the sludge is formed. So these are the different kind of equipments used in the primary treatment methods. So now coming to the lecture 29. So this lecture deals about the secondary treatment process. So we know after the primary treatment, the next step is the secondary treatment. So in the secondary treatment process, there are different methods involved. The first thing is it can be of different type based upon the air required. Whether the secondary treatment. So this secondary treatment is also called as the biological treatment, right? So it is going to use the microorganisms for treatment. So Based upon the air requirement, it is classified into two types. One is the aerobic and second one is the anaerobic. We all know aerobic means in the presence of oxygen. Anaerobic means in the absence of oxygen. So only anaerobic microorganisms are involved here. Whenever the aerobic treatment is happening, the product will be carbon dioxide, water, and the leftover biomass. And whenever anaerobic treatment is happening, since O2 is not there, it cannot form CO2. So it is going to form methane, which is CH4, right? And some amount of carbon dioxide will also be developed, but in lesser amount. Okay, and then the leftover biomass will be there. Next is the microbial growth rate. Since it uses many microorganisms, the growth of the microorganisms are again classified. It can be a suspended growth or it is an attached growth. If you see, we are using a impeller. We are using an impeller. So this tank is continuously mixed. Okay, so the microorganism will also be suspended in this water, right? They will also be floating. Whenever the reaction happens. There is a suspended growth process. And then when it comes to the attached growth process, it uses a stagnant filter. One of the examples for this attached growth process is the trickling filter. So what happens is, so in this filter media, there will be a lot of microorganisms. So microorganisms are getting attached to this filter media. So the water will be flowing in and the water will be passing through the media and the pure water will be collected here in the outlet. So in the media, there will be a microorganism attached to it. So these water containing the organic matter act as the food for the growth of the microorganism attached to it. So this kind of growth is called attached growth process and this kind of microbial growth is called as the suspended growth process. So in both the types, we are using a microorganism, but only the mode of growth is different. And the next one is lagoon system. So lagoon system is like a pond system. So in this pond, the depth will be nearly 1 to 2.5 meter and detention time. For a stagnant period of time, it is left undisturbed like for 30 to 180 days. So this is a lagoon system. And coming to aerobic, anaerobic digestion, as I said, aerobic involves oxygen. So one of the examples is activated sludge process, and anaerobic digestion involves absence of oxygen. It is like packed bed and trickling filter. Biofilter is a filter where the biomass is attached and it is used for filtration of the water. So these are the some equations required for problem solving. And if you see the microbial growth and retention time, the net growth kinetics is given as this is x. dx by dt is equal to mu x minus kd into x. Here, x is the amount of biomass, okay, and the growth rate is given by dx by dt. And the substrate utilization rate. Here, the substrate is what? Waste matter, that is the organic matter present in your wastewater is the substrate, like food for the microorganism. Okay, which is given as dsr by dt. And monod function, by using the monod mathematical relation, it is given as mu is equal to mu max into s divided by ks plus s. So ks is the rate at which the substrate is taken by the microorganism and s is the amount of substrate given initially, and then mu max is the maximum specific growth rate and mu is the specific growth rate. And yield coefficient is given by y is equal to dx by dt whole divided by dsr by dt. Specific growth rate, as I said, mu is the specific growth rate. Now the hydraulic retention time. For how much period of time the water is retained there during the process? is given by V by Q. V is the volume, which is the capacity of the particular tank or container, and Q is the flow rate of the wastewater. So the hydraulic retention time is given by V divided by Q. This is one formula. And theta C. Theta C is the mean residence time. This is for the sludge, how much time it is there. So theta C is equal to mass of the solid in the system, how much solid is there in the system, divided by mass of the solid leaving the system per day. So this is the theta C, mean reference time. And F by M is the food to mass ratio. So this is given by substrate removal rate by solid microorganisms in the system. So these are the formulas required for solid. And this is a table indicating the different type of lagoon system. Like a lagoon can be a aerated aerobic and aerated facultative, aerobic facultative, aerobic. The main difference is very simple. So the aerated aerobic means aeration of the pond is accomplished by use of mechanical oxygen diffusers. We are providing the oxygen. And sedimentation is also there. It is completely aerobic. And then aerated facultative. Facultative means it is containing both. Like it uses the surface aerators only, and at the bottom it will be having anaerobic decomposition. Okay. And then aerobic facultative is here the oxygen supply is provided like in aerated, but it is also mixed. And some anaerobic activity is there again at the bottom. So this is aerobic facultative. And aerobic is it is the shallow ponds where the microorganisms provide the oxygen to maintain the aerobic condition in the pond. No external oxygen is given. If external oxygen is supplied, it is aerated aerobic. If the oxygen supply is mainly by the use of the microorganisms alone, then it is aerobic. And facultative means both aerobic and anaerobic conditions will prevail based upon the oxygen supplier. Like if it is natural, it is aerobic. If it is externally provided, it is the aerated. Okay. So now we will see the process. Uh, these are the schematics of different secondary treatment process. So the first one is the lagoon system. As I said, it can be of different types like aerated aerobic, aerated facultative, aerobic facultative, and only aerobic. So if you see this one, Arabic is also there, anaerobic condition is also there. So it is definitely a facultative lagoon system. A lagoon is a pond stabilization system. So here the wastewater is stabilized. Uh, say for example, this is a pond. So this pond is completely maintained for a particular period of time. So what happens? This is the sludge. Sludge is formed at the bottom. Wherever the sludge is happening, here the oxygen is very minimum. So the organic matters will be converted by the anaerobic microorganisms as organic acid, and finally it is releasing the methane carbon dioxide as the gas. Okay, and then in the top, it is having the interaction with the gases. So oxygen is coming in contact with the waste matter. So these microorganisms naturally existing in the waters like bacteria, algae, also release the oxygen. External oxygen is also there. By using the oxygen, the aerobic decomposition occurs. So release of carbon dioxide will be higher in this above region. Okay, more amount of microorganisms will also grow here. So both aerobic and anaerobic conditions are happening in this kind of lagoon system. And then next one is the activated sludge process. So this is a secondary treatment process where the sludges are very much agitated. So this is the aeration tank. So it is agitated. By agitating it, like mixing vigorously, will produce the air molecules. So now with the help of gas molecules, the oxygen is supplied here for the growth of microorganisms. So this mixed liquor is then passed through the sedimentation tank and the process continues. So this is activated sludge process. And next is the aerobic digestion and anaerobic digestion. The main differences, as I said, the microorganisms are involved here with the presence of oxygen. Okay. So the products are all released. The growth of microorganism happens, and also the gaseous molecules will get released. Now, in the anaerobic digestion process, oxygen will not be there. That is a major difference. So when the wastewater is coming in, it is going to form a sludge here. So sludge granules will be formed here. Based on the pressure, extreme pressure conditions will be prevailing here since it's a very closed environment. And because of the external pressure, what happens here is it releases the biogas, which is methane. So anaerobic decomposition of the organic matter happens here. And then the effluent water alone will be collected outside and it goes to the next step. So these are the methods involved in the secondary treatment process. So this is the overview of your week 6 lecture. Do you have any doubt? Shall we proceed to assignment 6 sample questions? Audio is too low. Is it okay for everyone else or everyone or facing the same issue? Am I audible? Okay. Now coming to the assignment 6 sample question, dash or smaller in size particles while the dash or larger in size particle. Like the size is also mentioned. You know this one. So what is the size of the particle? Oh, sorry, name of the particle having the size 0.001 to 1 micron. And what is the name of the particle having the larger size of 1 to 100 micron? What is P and Q? Okay. The answer is P is the colloid and Q is the flock. So initially colloids will be there. They will be having the same charge. So afterwards the neutralization of the colloid molecules occur. So the minus plus charges will be there because of the addition of alum. And this particle is called as colloid and this particle is called as the flux. Okay. This will be smaller in size, this will be larger in size. This process is called coagulation. Next is identify the figure. What is A, what is B, what is C? Which is turbine chamber, which is propeller chamber, and which is paddle chamber. Any guess? Okay. The answer is A, or it is first one. So A is the turbine chamber. You can look at the diagram, the impeller. And B is the propeller chamber, and D is the paddle, or C is the paddle chamber. Okay, option is 1. Which of the following process is used in tertiary treatment of water? Tertiary is like next to secondary treatment, right? So which process is used in the tertiary? So tertiary treatment also involves ozonation and membrane separation. Depending upon the type of wastewater, ozonation membrane separation can be involved in tertiary treatment also. When there is no separate quaternary treatment, this comes under tertiary treatment itself. Next question is the treatment plant where effluents of a whole industrial cluster is treated centrally is known as what? On-site disposal, sewage treatment plant, effluent treatment plant, common effluent treatment plant. So the answer is very easy. Common effluent treatment plant. Why? Here the effluence of whole industrial cluster is treated. From all the industries it is treated, right? So it is CETP. That is the right answer. Next question is the biological treatment, that is the purification of wastewater, primarily by the decomposition of suspended and dissolved organic matter by microbial action, comes under which treatment they are asking. So it is the biological treatment. It uses the microbial action. So the answer is secondary treatment process. It only uses the microorganism, okay, for degradation of organic matter. Next is match the type of settlings with their appropriate description. Discrete settling, hindered settling, flocculent settling. Just now we have discussed. What is the right answer? Any idea? So we know that at different depth, different particles will be there. Finally, the compaction is there. We are leaving that area for compaction. And before this, we have mini region. This region is clear water. In this region, all the particles will be having individual settling velocities, that is corresponding to P. Okay, and this region again, particles will interact with each other, and it is called as the Q region, which is hindered settling. And here the flocks will be formed. So this will be very tightly packed. Larger particles will be there. So that is the flocculent settling. That is your R. Okay. So in the discrete settling, what happens? The right answer is 231. What happens is all the settling particles fall with their individual settling velocities, which are same throughout their entire fall. That is, each particle falls from equal depth in equal time. That is the first stage. This is your discrete settling. And in the hindered settling, what happens? Settling at a reduced speed. The speed will slightly decrease relative to single particle settling velocity due to the interaction with neighboring particle. Since they are interacting, here the velocity will be reduced. And then the flocculent settling. Settling velocity of the particle increases because due to the coalescence with other particles. Here the particles form the larger size, so it will settle faster. So that is the flocculent settling. Finally, this is the compaction. They all will get settled down at the extreme depth. So when the depth of the when the time of settling increases, the depth of the particle going to settle will also increase. Okay, that is the one thing you have to keep in mind. Next question is the tube settler increases the settling capacity of sedimentation tank by. So the tube settler is going to increase the settling capacity by increasing the velocity of particle, increasing the size of particle, reducing the vertical distance to which flock must settle, increasing the diameter of the tank. So if you increase the diameter of the tank, the settling capacity will not increase. And then if you increase the velocity of the particle also, um, in the tube settler it will not increase. So particularly in the tube settler, how it is going to increase, they are asking. So here it reduces the vertical distance to which flock must settle. By decreasing this distance, the settling is increased in the tube settler. Okay, so this is the right answer. Which of the following lagoon system has high operation and maintenance cost? So maintenance and operation cost is higher for aerated aerobic. So here you are supplying the external air. Okay, so external air is there, and it is not partially facultative also. Like no anaerobic decomposition happens. So the entire decomposition is going to happen in the aerobic mode. That too, not naturally. Externally, you are giving the more amount of oxygen. So it will be a high operation and maintenance cost involving process. So answer is aerated aerobic lagoon system. Now, coming to the problems, the question is for a continuous flow settling tank 3-meter deep and 55-meter long, what would be the flow velocity of water for effective removal of 0.03 mm particles at 25 degrees Celsius? The specific gravity of the particles is 2.65 and viscosity of water may be taken as 0.01 centimeter square per second. So the depth is D. The depth D is given as 3 meter and the length L is given as 55 meter and the size of the particle, the diameter of the particle. So you can see the depth as height. Here keep it as H. So diameter is given as 0.03 mm. It is in millimeter. Specific gravity is given as 2.65 and this is the weight of the particle, solid. And for water it is always 1, right? And then viscosity of the water mu is given, which is 0.01 centimeters square per second. So you need to calculate the flow velocity. So that is the question. So you have to calculate it by using this formula, which is Vs is equal to G into rho P minus rho into D square divided by 18 mm. So the diameter of the particle is 0.03 mm. It is in mm. So we know that 1 centimeter is equal to 10 mm. Right. So you convert the mm to centimeter divided with 10. So 0.003 centimeter. Why in centimeter means all the units should be kept as same. So it is given in centimeter per second. Now 9.81 this meter square per second, converting it as again meter per second is converted into centimeter. So 9.81, so 981 we have taken as G, which is constant. Rho P is 2.65 and rho is 1 gram per centimeter cube. And then the diameter of the particle is 0.003 the whole square, 18 mu. Mu is 0.01 centimeter square per second. So if you solve this one, you will obtain the PS as 0.08. Why we need to find the settling velocity? To find the flow velocity means we are going to find our flow velocity using this relation, okay, which is V by Vs is equal to L by H. So the only unknown thing is V. So now Vs is known. We know the length and we also know the height of the settling tank. Substitute them. L is 55, H is 3 meter. So if you substitute this one, so meter will get cancelled. Ps is in centimeter per second. The answer is 1.485 centimeter per second. This is the flow velocity. Okay. Answer is 1.485. Now the next question is a circular sedimentation tank fitted with mechanical sludge removal unit. So to the circular sedimentation tank, there is a mechanical sludge removal unit, which is to treat 4.5 million liters of water per day. So every day, 4.5 million liters of water are treated. The detention time of the tank is 6 hours. So 6 hours it is going to retain the water in it. If the depth of the tank, which is depth, so height is h, which is 3 meter. And calculate the diameter of the tank. D is unknown. That is what asked to find. And then the capacity of tank can be calculated. That is, volume can be calculated by using the given relation, which is d square into 0.11 plus 0.785 h. Here h is the depth, d is the diameter. To find this one, we know d is the unknown and we know h is given. Volume is to be calculated. Okay. How the volume can be calculated? Can be calculated with V is equal to Q into T, right? So Q will be in meter cube per second flow rate into time will be in second. So this will get cancelled. It can be meter cube per hour or meter cube per second into second. So whatever at the time, it will get cancelled. So we will arrive at the volume of the tank by multiplying the flow rate into detention time. This is how we have to calculate the volume. Since the volume will be known and the height is given, we can find the diameter easily. Okay. So this is how you have to solve. This 4.5 million liters per day. So 4.5 million. So into 10 power 6. So this is the flow rate Q. And this is the time. Out of 24 hours, 6 hours or 10 for the detention period. So multiply this, you will obtain 1125 meter cube. So this is the capacity of the tank. So the capacity of the tank is related with the given equation, like related with diameter, and it is given by the relation B is equal to T square into 0.11 plus 0.785 H. H is 3 meter substituted, and we will arrive at the D square value as 21.36 meter. Okay. Only thing is we have to first find the volume, then substitute all the known values to find the unknown diameter of the tank. Answer is 21.36. Do you have any doubt? Shall we move to the tutorial problems? So far, any doubts? We will move to the tutorial problems. Okay. Coming to the tutorial 6, so this problem is similar to the previous problem. Just now we have discussed this, but the data are only different. The question is a circular sedimentation tank fitted with mechanical sludge removal unit is to treat 4 million liters of water per day. So here the water is going to be treated. The flow rate is 4 million liters per day, which is 4 into 10 power 6. And then the detention time of the tank. So detention time is 5 hours. So 5 out of 24. And then if the depth of the tank is to be restricted to 3 meter. So H is given as 3 meter. And then calculate the diameter of the tank. D is to be calculated. The capacity of tank, that is the volume of tank, can be found using the relation volume is equal to D square into 0.11 plus 0.785 into H. This is constant, okay? Where H is the depth and D is the diameter. So now we are going to find the quantity, that is capacity, with V is equal to Q into T. Okay, so Q is 4 into 10 power 6, T is 5 by 24. So it will be in liters. You have to convert liters to meter cube. So you know, right? 1 meter cube is equal to 1000 liters. So whatever values you are getting, you have to divide it with 1000 to convert in the unit of meter cube. So the volume is 833 meter cube. And then h is given as 3 meters. So substitute it here and we will obtain the d square value as something, and again to calculate the d, take the square root of the value. So diameter of the tank is d is equal to 18.38 meter. This is the answer. This is the another question with similar data. So this is how we have to solve it. So here the question is a circular sedimentation tank fitted with a mechanical sludge removal unit. So here Q is given as 5 into 10 power 6. Okay, 5 million liters. And then the retention time of the tank is 5 hours. So T is 5 hours. 5 by 20. So whatever value you are getting is in liters. See, here it is in liters, right? So it is 10 lakhs 41,666 liters approximately. So to convert it to meter cube, we have to divide it with 1000. So it will be 1041.67 meter cube. This is the volume capacity of your circular sedimentation tank. Now we have to find the d square value with b is equal to d square into 0.11 plus 0.785 into 3 depth of the tank. So it is 2.465 d square. D is obtained by taking the square root of V, which is 1041.67 divided by 2.465. Answer is 20.556. So the nearest value is 20.59. So the answer is 20.59. This is how you have to calculate the diameter of the circular sedimentation tank using the given relation. First step is to find the volume capacity, and then we can use the relation to find the unknown diameter. The next question is also similar to the assignment problem. The question is for a continuous flow settling tank, 3 meter deep and 60 meter long, what would be the flow velocity of water for effective removal of 0.05 millimeter particle? So the diameter of the particle is given as 0.025 mm at 25 degrees Celsius. The specific gravity of the particles is 2.65 and viscosity of water may be taken as 0.01 centimeter square per second. So unit conversion is very important. Question asks us to find the flow velocity. We know the relation, right? V by Vs is equal to L by H. So L is given already, which is 60 meter long, and the H is given, that is 3 meter deep, and we need to find the V. For that, Vs is important. To find the Vs, we are going to use this relation. Okay, so substitute the known values G is 981 in centimeters, and then rho P minus rho. So here 2.65, rho is the liquid medium, which is water. So it is 1. Specific gravity is 1. And then dp square. So it is in mm, again converted. So 0.0025 centimeter square whole divided by 18 into 0.01 centimeter square per second. So now all the units are in same centimeters. So your Vs will be 0.0562 centimeter per second. So now what you have to do, substitute the Vs obtained here in this formula, and then you will obtain the V value, which is the flow velocity. So your flow velocity is 1.125 centimeter per second. It should not be more than this. Okay. This is a similar type of question, but the given data are a little different. The question is, for a continuous flow settling tank 3 meter deep and 90 meter long, what would be the flow velocity of water for effective removal of 0.025 millimeter particles at 25 degrees Celsius? The specific gravity of the particles is 2.65 and the kinematic viscosity of water may be taken as 0.01 centimeter square per second. Assume the laminar flow in the tank and density of water as 1 gram per centimeter cube. Okay. So now the only difference here is instead of viscosity, they have given you the kinematic viscosity. You cannot take this viscosity directly and solve the problem. Then your answer will be wrong. Okay. So to convert this kinematic viscosity to viscosity, we have to multiply it with the particle density, okay, which is rho. Here, um, this is the viscosity of the water. So here the particle is your water and the rho value of your water is 1 gram per centimeter cube and your kinematic viscosity is given in question. Mu chem is 0.01 centimeter square per second. And we are converting this centimeter square to meter square. We know 1 meter is equal to 100 centimeter. So this is centimeter square. So 100 into 100, just 10,000. And then you are converting the gram to kilogram. We know 1 kg is equal to 1000 grams. Substituting it. And again the centimeter cube is also converted to meter cube. Okay, so we are converting everything in grams and in kgs and meter. So now we are a new viscosity. This is the viscosity of water. This is not the viscosity of water. This is kinematic viscosity. So our new value is 0.001 kg per meter second. Since we have obtained the mu value, it is very easy to find the Vs value. So Vs is equal to G into rho P minus rho into dP square divided by 18 mu, right? So here G is 9.81. Again, it is in meters and seconds. And the particle specific gravity is given as 2.65. Okay, this is in gram per centimeter. In the case of kg and meter cube, it is 2650. Minus for water, it is 1000 kg per meter. And then the diameter is given as 0.0025 mm. So convert it to meter. So it is 0.025 into 10 power minus. So again, all the values are converted to meter divided with 18 mu. So 18 into mu. So a mu value is obtained from the kinematic viscosity, which is nothing but 0.001 kg per meter second. So solve this one to arrive at the settling velocity of the tank, which is in the unit meter per second. So now you know the relation, which is we know that V by Vs is equal to H by L, right? That is given here already. L by H. V by Vs is equal to L by H. So the same relation is used here to find the V value. So now the depth is 3 meter, length is 90 meter. So 90 by 3 into your settling velocity will give you the flow velocity, which is nothing but 1.68 centimeter per second. So this is your answer. So only difference between the previous problem and this problem is the kinematic viscosity is given. To convert the kinematic viscosity to viscosity, multiply it with the specific gravity of the water and then this one, 1 gram per centimeter cube. So you will obtain the mu. Always keep the units in centimeter or keep the unit in meter. It is well and good so that no confusion will be there. Now the next question is drinking water treatment plant uses a circular sedimentation basin to treat 5 mgd. So this mgd stands for million gallons per day. Okay, and the unit conversion to convert the mgd to meter cube per second is also given. So 1 mgd is equal to 0.0438 meter cube per second. So a drinking water treatment plant uses a circular sedimentation basin to treat 5 mgd of river water. The river often carries 0.01 mm silt particle. This is the silt particle size. And the average density of the silt particle is 2.2 gram per centimeter cube. The silt must be removed before the water can be used. The plant's clarifier is, so this tank, clarifying tank depth is given as 5.5 meter and its diameter is given as 25 meter. So here in the question, diameter is given already. The water is at 15 degrees Celsius. The water density and viscosity at 15 degrees Celsius are found to be 9099.1 uh, 999.1 kg per meter cube and 0.00114 kg per meter second. Okay, note down all the units are in kg per meter cube and kg per meter second. So we need to convert them accordingly. So the question is to find what is the hydraulic detention time. They are asking you the hydraulic detention time theta. And then will the clarifier remove all the cell particles from the water? So this is part A, this is part B. So to find the part A, which is the hydraulic detention time theta, the formula is theta is equal to V by Q. V is the volume of the vessel and Q is the flow rate. We already know the flow rate, which is 5 mgd, right? So just convert it to meter cube per second by multiplying it with 0.0438. So that is how you will arrive at the Q value. Then V. This is a circular basin, right? So this is a circular basin. So you can use the formula pi r square h as the volume of the basin. So now instead of r, the diameter is given. So r square can be written as d square by 4. Okay, that is how this formula is arrived. Since we know the diameter of the basin and also the depth of the basin, pi and 4 are constant values. So now you can substitute this b value in this equation. That is how this equation is obtained. So theta is equal to pi d square h divided by 4q. Substitute all the known values here. Pi into 25 meter square. It is given here and then h is 5.5 meter divided by 4 into q. Q is 5 into 0.0438 meter cube. So we'll obtain the answer in seconds since the flow rate is in meter cube per second. You have to convert this to hour. For that, you have to divide this value with 3600. Right. So 1 hour is equal to 60 minutes. 1 minute is equal to 60 seconds. So 60 into 60 is 3600. So theta is equal to 3.42 hours. So the first part is completed. So hydraulic detention time theta is found. The second part, the question is, will the clarifier remove all of the silt particles from river water? To answer this question, you need to find the critical velocity. So you need to find the critical velocity of the basin and you have to compare the settling velocity of the particle. Okay, so you need to find these two things. So we know the settling velocity formula is Bs is equal to G into rho P minus rho into dP square divided by 18. G is constant 9.807 meter per second square and rho P is given as 2.2 gram per centimeter cube. So converting it, so 2200 kg per meter cube and the density of water is given as 999.1 at 15 degrees Celsius and mu is 0.00114. Okay, all the known values are substituted here and the diameter of the particle is given as 0.01 mm. So dP is 0.01 mm. Okay. So already two digits were after the point and mm is 10 power minus 3 meter. So 10 power minus 5 meter is substituted here. So if you solve this one, you will obtain 5.74 into 10 power minus 5 meter per second. So this is the settling velocity. Now to find the critical velocity, critical velocity. So the critical velocity is the velocity, overhead velocity, where the overflow can happen. Okay, that is the critical velocity of a sedimentation basin. So P naught is equal to h divided by theta, which is equal to 5.5 meter. We know the depth, and theta is obtained as 12,321. Right. We are substituting this value here. So the critical velocity is 44.63 into 10 power minus 5 meter per second. We need to compare the Vs along with V naught. So V naught is very much greater than the Vs. So the sill settling velocity is much less than the basin's critical velocity. So all the cells will not be removed by the treatment plants clarified. That is the answer for your part B. Okay. Do you have any doubts so far? Any doubts so far? The next question is similar to the previous question. The drinking water treatment plant uses a circular sedimentation basin to treat 5 mgd of river water. Again, the conversion is given in the question itself. The plant's clarifier is 5.5 meter deep, 15 meter in diameter. Water is at 15 degrees Celsius. Water density and viscosity at 15 degrees Celsius or 999.1 kg per meter cube and 0.00114 kg per meter second respectively. What is the hydraulic detention time of the clarifier? So the question asks us to find the hydraulic detention time. We know that theta is equal to V by Q. Okay. Now to find this, you know the flow rate, which is 5 mgd, and you want to find the volume with the specifications given. So we know V is equal to pi d square by 4 into h. Diameter is 15 meter, so 15 square. H is 5.5 meter depth. So it is substituted. So volume is calculated, which is 971.93 meter cube, and Q is 5 mgd. So 5 into 0.0438 is 0.219 meter cube per second. V is calculated, Q is calculated. Just divide V by Q, and then you will obtain the value 1.23 hours. This will be in second. So converting it to hours, so the answer is 1.23 hours. This is a simple problem. Now, coming to the next problem, it is about the hardness of the water. As I said earlier, this hardness is mainly caused by uh, two elements, which is the calcium and magnesium. So the question here is a sample of groundwater has 150 mg per liter of calcium and 20 mg per liter of magnesium ions. Express the hardness in units of milli-equivalent per liter and mg per liter as calcium carbonate. Two questions are asked. First, they ask you to find the hardness, but in two different units. One should be in the unit of milli-equivalent per liter, and another one is as mg per liter as calcium carbonate. They are asking. Okay, and the molecular weight of calcium is 40.1, mg is 24.3. Equivalent weight of calcium is 20 mg per milliequivalent, and magnesium is equal to 12.2 mg per milliequivalent. It is treated in an adsorption unit, and 80% of hardness is removed. Calculate the hardness of the treated water. So the question is very simple. First part is to find the milli-equivalent per liter. So this milli-equivalent per liter is obtained by dividing the mg per liter and mg per milli equivalent. So what happens here is mg will get cancelled and milli equivalent per liter will be obtained. This is the formula. So what is mg per liter? Mg per liter is the concentration of the X component. Okay, that is the concentration mg per liter. And what is mg per milli equivalent? So this mg per milli equivalent is the equivalent weight of the particular component. Okay, that is already given. So both the concentration and the equivalent weight are given. You have to just divide the concentration and with the equivalent weight to arrive at milli equivalent per liter. So for the case of calcium, the concentration is 150 and the equivalent weight is 40. Equivalent weight is 20. 40 is the molecular weight. So 150 divided by 20 is 7.5. So in the case of magnesium, the concentration is 20. So we have to divide 20 with the equivalent weight of 12.2. So 20 divided by 12.2 is 1.63 milli equivalent per liter. Okay. So the first part is over. Hardness is found in the unit of milli equivalent per liter. Next part is to find the hardness in the units of mg per liter as calcium carbonate. So it is very simple. Now we know the values of milli equivalent per liter, right? So this is known one. Just convert it to mg per liter by multiplying it with 50 mg. So this 50 mg milli equivalent corresponds to the calcium carbonate. Okay. So they are asking you to express the hardness in terms of calcium carbonate. Okay, so you have to multiply it with 50 mg per milli equivalent. So milli equivalent will get cancelled. So this is the mg of calcium carbonate per liter. Okay, so now you know it is 7.5 milli equivalent per liter for calcium. So just multiply 7.5 into 50. We will obtain 375 mg calcium carbonate per liter. And then we have to multiply this 1.63 mg per milli equivalent per liter into 50. So we will obtain 81.96 mg of calcium carbonate per liter. So the second part is also over now. Then the question is, it is treated in an absorption unit and 80% of hardness is removed. So 80% is already removed. They are asking you to find the hardness of the treated water. How much hardness is there in the treated water? So if 20% is removed, if 80% is removed, only 20% will be remaining, right? So first find the total hardness. So total hardness is nothing but the summation of the calcium plus magnesium. So for calcium, it is 7.5 milli equivalent per liter, and for magnesium, it is 1.63 milli equivalent per liter. So now the total hardness is 9.13 milli equivalent per liter. You know that again in terms of calcium carbonate, just add these one 375 and 81.96. So it is 456.96 mg per liter calcium carbonate. Okay. So now you know 80% is removed, 20% is left out. How much is the 20% of the total hardness? So multiply it with 0.2. So after treatment, the water hardness is 456.96 into zero point 0.2 gives 91.39 mg per liter. So this is the amount of hardness present in the treated water. Okay, it's very simple. all the data are given. First, you need to find milli equivalent per liter by using this formula, and you have to convert them to mg per liter as calcium carbonate by multiplying it with 50, and then you have to add the calcium and the magnesium hardness to arrive at the total hardness. Now the removal percentage is given, so multiply it with 0.2 to find the amount of hardness present in the treated water. Okay. The next question is, a town of 50,000 sends 0.5 meter cube of wastewater per person per day to the wastewater treatment plant. So number of persons living in the town is 50,000 and per person is generating 0.5 meter cube of wastewater. So the total wastewater generated is 50,000 into 0.5 meter cube. Okay, that is the total wastewater generated in the town per day. So this gives the flow rate of the wastewater from the town. So this much amount of wastewater is sent to the wastewater treatment plant. A conventional circular primary clarifier would be designed to have an average detention time of 2 hours. So the detention time is given as 2 hours and the average overflow rate. So overflow rate is given as 45 meter per day. What would be the dimensions of a conventional filter? So here they are asking the dimension. Dimension is nothing but what would be the diameter, what would be the area, what would be the height. All these things you need to calculate. Mainly the dimension is the depth of the clarifier. Firstly, with the data given, find the flow rate. So the flow rate is 0.5 meter cube per person per day. Then for 50,000 people, it would be 50,000 into zero point 0.5, which is 25,000 meter cube per day. Since we know the flow rate Q, which is 25,000, we can obtain the area of the clarifier. So the surface area of the clarifier is given by Q divided by V naught. V naught is the overflow rate. So the overflow rate is 45 meter cube per day. So substituted 45 meter per day. Substituted, so you will obtain 555.55 meter square as the surface area. Now we know the surface area. With this, the diameter of the tank can be calculated by using this relation. Just square root of 4 into surface area divided by pi. Substitute this answer here. So the diameter is obtained as 26.6 meter. Since we know the diameter and also the surface area, we can easily calculate the depth because we know that theta is equal to V by Q, right? And we know V is area into height. So theta is given, Q is given, H is the only unknown thing you need to find, and A is also found now. So substitute everything here. So H is equal to, rewrite this equation, H is equal to Q into theta. H is equal to Q into theta divided by area. So Q is 25,000 meter cube per day, theta is 2 hours, and A is 555.6 meters square. So this is in hours. We are converting it for per day because the flow rate is for per day. So divide it with 24. The final value is 3.74 meters, which gives you the height of the that is the depth of the clarifier. Okay, now we have arrived at the dimensions of the clarifier. We found the diameter and also you have found the H. So with the volume you can find only the depth, height and the diameter. So if they ask you for the diameter, just find the, if they are asking you for the dimension, calculate only the diameter and the depth. Okay, this is the unknown. Now, coming to the last problem, the question is an aerated activated sludge tank. So here it is an activated sludge tank is being operated under the following conditions. So Q is equal to 4400 meter cube per day. Flow rate is 4400 meter cube per day. MLSS, it is the mixed liquor suspension system. So amount of microorganisms there is 3500 mg per liter. Okay. And then Y is zero point 0.5. And then tank volume. Volume is given as 770 meter cube. The rate constant is Kd is equal to 0.09 per day. First question is to estimate the weight of the solids produced per day for the conditions in which the BOD is reduced from 350 to 130. So weight of the solids they are asking. And then next question is estimate the theta C. Theta C is the retention time. Next is to estimate the F by M ratio, food to microorganism ratio they are asking. So since we know the tank volume V and we know the flow rate Q, it is very easy to find the hydraulic retention time. So the hydraulic retention time is P by Q, which is equal to 770 divided by 4400 uh, meter cube per day. I will write it here. This is in meter cube. This is in meter cube per day. So it will get cancelled and you will obtain the HRP as 0.175 days. Next one is you are finding the weight of the solids in a day. So dx by dt is equal to, this is the standard relation. Okay. dx by dt is equal to y into dsr by dt minus kdx. So y is already given, y is 0.5 dsr by dt. So change in the amount of substrate concentration is mentioned already, which is 350 to 130. So 350 minus 130 and the time taken is obtained, which is 0.175 days. Okay. Next is KD. KD is given already, which is 0.09 into X. So X is the initial amount present there. Initial amount is 3500. So this is the X biomass, 3500. If we solve this one, we obtain 313.57 mg per liter per day. Okay. So now the next question is to find the theta C. It is the mean residence time of the sludge in that activated sludge tank. How long it is there in the tank. So it is obtained by theta C is equal to mass of the solid in the system. So the solid is nothing but the biomass. So that is X. And then mass of the solid leaving the system per day. So this is dx by dt net. How much it is leaving per day. Okay. This can be found indirectly by using this relation. If you see this one, this is dx divided by dx by dt, right? We can write the theta c, this equation as this. Theta c is equal to x divided by dx by dt. You already know the relation of dx by dt. We can write this 1 by theta c is equal to 1 by theta c is equal to dx by dt divided by x, right? You can write it like this. So this can be written as 1 by x into, we can write the dy by dt as this y into s naught minus s, which is nothing but dsr, and then divided by t, this time minus kd into x. If you multiply this x inside, what happens? there will be y into s naught minus s divided by t into x will be there, and this x and this x will get cancelled, and you will obtain only minus kd here. Okay, now this is your 1 by theta c. This is how this equation is derived. Now 1 by theta c is equal to y into this s naught minus s divided by t divided by x. It can be written as f by m. This is the equation. Okay. So now substitute the values. S naught minus s is 350 minus 130, and the time taken is 0.175 divided by x is 3500. Then you will obtain the value of 0.359. So this is the food to microorganism ratio. So C is calculated. So A is also calculated. Now only thing left out is the theta C. You know 1 by theta C is equal to y into f by m minus kd. So substitute this value 0.39 here. Y is equal to 0.5. It is already given in the question. So I am solving it here. 1 by theta C is equal to y is 0.5 given in the question into f by m is 0.359. 359 minus, so first we need to multiply this one, minus kd. Kd is constant, which is 0.09. So to solve this, we'll obtain some 0.008 something. So if we take the reciprocal of this one, we will obtain theta c is equal to 11.17 days. This is how the theta c, which is the mean sludge retention time, is calculated. So it is derived using this equation. If you see, the time taken is calculated by v by q, and dx by dt is equal to y into dsr by dt minus kdx is a general formula. We are substituting everything and calculating the weight of the solid produced per day in this condition. Then theta c can be also written by using this formula. Theta c is equal to x by dx by dt. We are rewriting this to this equation, and this dsr by dt divided by x is known as f by m. So calculate it, substitute it. So 1 by theta c is obtained, f by m is also obtained. Take reciprocal of this and obtain the theta c value. This is how this problem is solved. So thank you. Do you have any doubts in the problem? Okay. Thank you for joining today's session. See you all in the next session on next Saturday from 3 to 5 p.m. You can use the same link, and this presentation this presentation will be uploaded in the Drive link, and this lecture is recorded, so it will be uploaded in the YouTube. You can find it later. Thank you for joining today.